Welcome back, everyone. We are starting chapter 3 today, and finally we can actually do some actual calculus. For those of you that remember calculus, we're going to actually get to do that. So I want to point out that when we're talking about the first derivative, we're talking about the slope of the tangent line. And you can see it's a horizontal line when the slope is equal to 0, meaning y is equal to a constant. And I want to start out over here. I want to take the first derivative, that's f prime there, using our definition way of doing this. And if you recall, f prime of x is going to be equal to f of x plus h minus f of x all over h. And I'm going to go ahead and FOIL that out. And I'm going to notice the x squareds, plural, both go away. Oh, and I did a no-no. The limit as h approaches 0. Limit as h approaches 0. And you'll notice I can factor an h out from there. And of course, this allows us to reduce out the h's. And you'll note when h equals 0, I can now plug that in. I just get 2x. So the derivative of x squared is 2x. And I could do the same thing, use the definition. But when I take the derivative of x cubed, I'm going to get 3x squared. And I could do the same thing with x to the 4th as I did over here with the definition. And I'm going to get 4x to the 3rd. And even the 5th one, 5x to the 4th. And you might be noticing a pattern at this point, which is because there is a pattern. So if we have the nth power, and we're taking the first derivative, we're going to get n, that's what the exponent was, times x to the n minus 1 power. And you can see that. When it's x squared, the 2 comes down in front, and we subtract 2 by 1 to get first power. 3 comes down in front, we subtract the exponent by 1, we get second power, and so on. Now, this is a big deal. I want to be perfectly clear. This is our first taste of what I call real calculus. It's all calculus that we're doing, but this is, to me, the differentiation without having to go through all of this now. So let's practice using this rule. And I'm going to go to example 1 here. And I'm going to rewrite this one as x to the negative 2 power. And you can see now n is negative 2. So using the rule, so f prime is in this case negative 2 times x to the negative 2 minus 1, which is negative 2 times x to the negative 3rd, or negative 2 over x to the 3rd. All right. Part B, let's use a different color because we got a little out of control there. This is going to be x to the 2/5 power. If you remember your exponent rule. So f prime of x is going to be 2/5 times x to the 2/5 minus 1, which is x to the negative 3/2. And I'm going to go ahead and stop there. We could actually simplify that a little bit and even use some radicals and stuff, but this is totally fine here. Now, example 2 is we're looking for the equation of the tangent line to this curve here. Now, I want to point out that this is y x times x to the 1/2 power. And if you remember, that's actually x to the first power. You add the exponents. And so that's going to make the derivative a whole lot easier. So m, or the slope, is y prime, which is 3/2 times x to the 1/2 power, because 3/2 minus 1 is 1/2. And I'm going to evaluate this at x equals 1 from here. This gives me 3/2. There's my slope. Now, that's just the slope. We want the entire equation. This is going to be y minus 1 equals 3/2 times x minus 1. This becomes y equals 3/2 x minus 3/2 plus 1. So y equals 3/2 x minus 1/2. And here's the equation of the tangent line at the point 1, 1. Not too hard, especially with our new rule here. It's very nice. All right, a few rules that we have. The derivative of a constant c is always going to be 0. And number 2 is our new rule. Now the third one, if I have a constant times a function, I can actually take that constant outside of the derivative. And I'm going to change this fourth one a little bit. It says plus, I'm going to make it plus or minus. Well, this is going to become derivative with respect to x of f of x plus or minus derivative with respect to x g of x. Meaning we can break them up when we do that. So for example 3, when we want to do the derivative, I can just treat each one individually as I walk through this. This is going to become 8x to the 7th plus 12 times 5x to the 4th minus 4 times 4x to the 3rd plus 10 times 3x to the 2nd minus 6, and that's going to be x to the 0, so I'm not going to put the x to the 0, is just 1. And the derivative of a constant we just learned is 0. So technically that's plus 0. So let's see what we end up with. There it is. It's a minus there. All right. The next example. Find the points on the curve y equals x to the 4th minus 6x squared plus 4, where the tangent line is horizontal. If you remember, horizontal means that the slope equals 0. So let's find the slope using our rule here. Minus 12x. Remember, the 4 goes away, it's a constant. And we want to know when this equals 0. All right. So let's see, let's factor out a 4x. And it looks like when x equals 0, when x equals root 3, and when x equals negative root 3. So let's find out what y is. I'm going to plug that into here. In fact, let me remind you how to do that with your calculator. If you go here, and we can type in the original, x to the 4th minus 6x squared plus 4. And I'm going to evaluate that here. If you remember, I go to vars, y vars, function y1, and I'm going to evaluate this at 0. And I expect to get 4, and I did. So one of the points is 0, 4. Let's do it again. We'll evaluate that at the square root of 3, -5. So we have root 3, -5 is our next point. Let's do it again. Vars, y vars. You can do this by hand. You don't have to use the technology like this. And also -5. I actually knew that this is an even function, so we can tell right away. And so this is going to give us -root 3, -5. So here are 3 points where the tangent line has a 0 slope. All right, on to page 2. Okay. Exponential functions. Okay. Now, what's going to happen here is we are going to note that the point of interest is here, 0, 1. And what we are looking for is the tangent slope. Remember, that's where it touches at exactly the 1 point. So what I'm going to do is I'm going to use our definition. Our function here is y equals 2 to the x power. So y prime is going to be the limit as h approaches 0 of 2 to the x plus h minus 2 to the x. And I want to point out that x is 0 in this case. Here, 0. This is all over h, of course. And then at x equals 0, we get the limit as h approaches 0 of 2 to the h minus 1 over h. Now I want to show you something. We can't directly plug in 0. We definitely have an issue there. So here's what's going to happen. I'm going to plug this in. This is going to be 2 raised to the, I'm going to call it x. I know it says h, but it doesn't matter. Oh, I need parentheses. Insert parenthesis. Minus 1 divided by x. And I'm going to choose a number really close to 0. So vars, y vars function. So let's pick point 1. We'll start there. Okay. We definitely have an ugly number. That's less than 1. Let's do it again, but let's get even closer. Vars, y vars. Let's go 0.00001. Okay. We're definitely getting closer and closer to 0.693, it looks like. Let's do it even closer. Vars, y vars. 0.00001. Okay, so it looks like we're converging to this specific point here, 0.6931. So this limit here is about 0.6931. Not quite 1. I'm going to also do y to the y equals 3 to the x power. So you can see we're going to end up with 3 to the h minus 1 over h. Right, it's the same work. So let me go ahead and fix that. turn that to a 3. Now that, let's do it again. And here's a cool feature. Now that I've changed y1, I could just hit enter and it'll do this for me. Okay, so this looks like it's about 1.0986. Now here's the thing. I did 2 to the x, I did 3 to the x. E, if you remember what E is, I will show you. E is above the division symbol on this particular calculator, so I can do second E, and it's 2.7 and change. Notice that's between 2 and 3, right? 2 to the x, 3 to the x. This is definitely between that. And I want to show you something really kind of cool. You'll note when we're using e to the x, that y prime is going to be the limit as h approaches 0 of e to the h minus 1 over h. And I'm going to go ahead and change that in here. So it's now e. And watch what happens when I evaluate bars, y bars. It's exactly 1. That is the beauty of e to the x. E to the x is very powerful. What that means for us is when we go through and we do the full-on derivative, we're going to have that y equals e to the x means that y prime is also e to the x. So this is the only function that when you take the derivative, you get the same function back. And what we're saying with this is that this slope here is exactly 1, which is pretty cool. All right. So we are going to find here the derivative of this function here. And so f prime of x, e to the x derivative, we just found out is, again, e to the x. And here, this is minus 1x. This is actually just minus 1. All right, now the second derivative means I'm going to take the derivative of the derivative. This here. Derivative of e to the x, again, is e to the x. Minus 1, that's a constant, it's gone. So here are our first derivative and second derivative. And there are uses for second derivative, and in second semester calculus, you'll have to take the derivative maybe 10 times. So you can kind of see the pattern and so on. But you don't have to worry about that for now. All right. Let's move on. At what point on the curve y equals e to the x is the tangent line parallel to the line y equals 2x? Here's the key. We're looking for a slope of 2. Now, we're looking for the point on the curve with a slope of 2. So let's draw a little picture, just to get an idea of what it is that we've been looking at here. And what we are looking for is that point where the slope is exactly 2. Remember, slope is rise over run, so up 2 over 1 is what this would mean. All right. So first of all, we know that the derivative is going to be e to the x. And we want to know, because the derivative of e to the x is just e to the x, when that's going to equal 2. Well, using some logarithms, I'm going to get that x equals the natural log of 2. Remember, the base of a natural log is e. E, once again, is that weird number 2.71828 and so on. It's called a transcendental number or an irrational number. It's like pi goes on forever and there's no pattern. We can't write it as a fraction, a rational fraction. So here's my x coordinate when this is the case. To find the y coordinate, that's going to be e to the x, ln of 2. Well, if you remember your logarithms, that just collapses out. We just end up with a 2. So what is the point where this happens? It's at the point ln of 2, 2. Meaning, this is ln of 2. Now, just to be clear, that's a number. ln of 2. 0.6931 and so on. So it's a number. It's not a very nice number, but it's a number. And this point here, the y coordinate is 2. Kind of cool. All right, last part. The second derivative of f looks like this. We have lots of different notations. We have y prime, double prime, I should say, f double prime of x. We could say f and put a 2 in there, and I'll show you where that notation comes from in just a moment. And the Leibniz notation looks like that. And if we want the nth derivative, meaning we need to take the 15th derivative or whatever it is, and you can see with e to the x, it's going to be the same every time, right? So the nth derivative looks like this. And that is an introduction to derivatives.